All right, so when we look at these exponential functions, we'll be right back after a short message from our sponsors. Everybody get that? No, we're not graphing. Not yet. We're just entering it. Everybody good here? Next one, 0.6 raised to the x, but now x is 3 over 2.
Is the whole answer, is the whole, all the numbers your answer? You don't round?
Well, yeah, we're not rounding yet. I mean, this is just an intro. We're making sure you know how to use the calculator, how to get to the exponent. I mean, this you're not going to have this is not rocket science right here. We're just making sure we can plug this into the calculator. That's all we're doing right now. How you do a fraction? You click the division button. Division is a fraction. There is no fraction button on these calculators. Again, and that's why we're doing this. All right, and D part, 1.05 raised to the 2 times x, which x is 12. So do that, I get 3.2250999944. Okay. Function and exponential growth problem would look like. Right, so these exponential functions, they have horizontal asymptotes, just like our rational functions did. Okay, but they don't have vertical asymptotes. So when we look at that graph, let's think about some of the characteristics that are happening. So again, this is not something you have to do every time. Let's just get a general idea. So what do we normally do to graph? Well, we pick some x values and we find out what the y value is. So if I plug in -2, -1, 0, 1, 2 for x and plug them in, okay, what is 2 raised to the -2nd power? That is a quarter, 0.25. 2 raised to the -1st power is a half, 0.5. So if you think about it, at -2, I'm at a quarter. At -1, I'm at 0.5. So we're increasing here. 2 to the 0. All right, do you guys know what 2 to the 0 is? Y'all don't know.
0.
It's 2.
One.
It's 1.
0.
It's 2. It's 1.
Play.
Okay, so we had to establish what something to the 0 power is. So the way that we picked, yes, okay, but I'm going to explain why it's 1. It's 1. You're right. It's 1. It's 1. It's 1. Thanks. Okay, so we use a base 10 system. You know what I mean by base 10 system? You learned about it when you were in, I don't know, 5th grade. You first learned about decimals, and they were the tenths, hundredths, thousandths. Okay, so what are all our place values? We start with ones place, and then we have the tens, and then we have the hundreds, and then we have the 1,000, 10,000, 100,000. You get the idea. Then after the ones, we have the tenths, and then we had the hundredths, and then we had the thousandths, 10,000, 100,000. Okay, so if we think about where they're at, the tens place. Okay, well 10 is just 10 to the 1st power. The hundreds place is 10 times 10, which is 10 to the 2nd power. Thousands place is 10 to the 3rd power. So the next one's going to be 10 to the 4th. You follow the pattern. I mean, that's what those place values are. Okay, now what's a tenth? Well, a tenth is 1 over 10. which is 10 to the negative first. What's 100th? That's 1 over 100, which is 10 to the negative second. Y'all know how negative exponents work? You remember negative exponents?
No.
Okay, so if I had x raised to the negative fifth, I can rewrite this as 1 over x to the fifth. If I have 3 to the negative second, that's the same thing as 1 over 3 to the second, which is 1 over 9. Negative exponents can go to the denominator, they change their... So, same idea here. 1 over 100, that's the same thing as 1 over 10 squared, which is 10 to the negative second. 1/1000th, so 1,000th, that's 1 over 10 cubed, which is 10 to the negative third. So if you look at the progression of the powers, it just made sense that a ones place be 10 to the 0. Anything to the 0 power is 1. Almost. That's almost true.
Really?
Now,
Almost. So what's the other?
okay, what's 0 to the 5th power?
Add that in for you.
0. What's 0 to the 2nd power? 0 to the negative 100th power. So what's 0 raised to any power? But what's anything raised to the 0 power? So then, what wins?
0 to the 0 breaks reality.
I win.
Yeah, let's just find out here.
Yeah, go ahead.
0 to
When you find out, let me know.
error. What do you think? What's your opinion?
It does both.
It's both.
It's 0 and 1, depending on what branch of math you're studying.
Branch of math.
That's the tree
Oh, I'm going to be without you on Wednesday, November 10th and Friday, November 19th. Because of the Chick-fil-A Leader Academy. Nice. So on that Friday, that's the day I'm giving a test. That's definitely... Yes, Friday the night, November 19th.
Like, is it an all-day thing?
I don't know. I just got a text.
Well, I'll tell them
It says, will this be an issue? If so, let me know and I can get with them later. So, the 10th, I mean, whatever. You might miss, I mean, that's Wednesday. I'm going to teach, or we might be working in class. But the 19th will definitely be the test day, because that's the last day before.
Can I just take it that Thursday?
Yeah. Take it
That's
Thursday.
probably what I'll do.
Just letting you know, I just got, that's again why I asked, because I figure this kind of stuff's fixing to start happening. People are just going to have stuff they don't know they got to miss for. I said, you obviously didn't know. Just knew right then. Okay. So, don't get me sidetracked. So what did we talk about? We talked about, let's see, we were saying -2 was a quarter. If I plugged in -1, I got a half. If I plugged in 0, I got 1. If I plug in 1, I get 2, right? 2 to the first power is 2. If I plug in 2, I get 4. So, I mean, what's fixing to happen? It's fixing to explode, right? It's fixing to be...
Yep.
So, to talk about, I mean, you can see graphically that it's fixing to take off. It's kind of like, I used to show this example to my 7th graders. I need you, we're fixing to start working at the Field of Nightmares. I mean, the greatest gift ever. And I need you I need help. I need to hire you for 3 weeks, 21 days, to come work the field. So the way I'm gonna pay you, I'm gonna give you 2 options. I'll either pay you $1,000 a day. It's gonna be hard work. I'll pay you $1,000 a day for every day, so $21,000. Or I'll give you a penny your first day you work, and I'll double it every day. You get 10 seconds.
$1,000.
Which one you want?
$1,000 a day.
Penny.
I'll be rich.
In 21 days, he said, a penny.
Oh, wait, I thought you were being serious.
I'm gonna get $1,000 a day.
You think if he had that much
I
money,
was
he'd give it
so
to us?
bad.
So obviously, you're set there. You start thinking. You start saying, okay, so I'd make a penny, 2 pennies. Give me the 1,000. Okay. Well, you made a bad decision.
Why? How?
Okay, because let's go through it. So if the first day you make a penny, well, that's going to seem really useless. But the next day I double it, so you'll make 2 cents. Think about it. You really bring the dough down. Then if I double it again, you're going to make 4 cents that day. So how much have you made? You've now made 7 cents
6, 7, yeah.
total.
I can math.
Okay. Then the next day I double it again. You make 8 cents. So now how much have you made total? You've made 15 cents total. So the way to figure out how much you make is if you double it, you always subtract 1 cent. Right? So we can see that pattern is going to keep going. Okay, so this is 1, 2, 3, 4. So on day 5, I double it, you made 16 cents. Well, you're probably going to quit this job real quick. On day 6, you made 32 cents. And on day 7, you made 64 cents. So you now have $1.27 for working for me for a whole week. Most people quit at that point, so we're good. But you're fixing to break a big barrier on day 8. You've now broken the dollar barrier for the day. Congrats. And then day 9, $2.56. Day 10, you make $5.12. Still not great. Day 11, $10.24. So you made about $20 so far. And I mean, you did okay, I guess. That's what day I'm on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's day 11. Day 12, you make $20.48. Day 13, you make $40.96. Day 15, you make $81.92. Day 16, you make $163.84.
Hurt me up a day.
Day 17, you make $327.68. Day 18, you make $655.36. Day 19, you make $1,010.72. What am I on? Day 20, I may have given y'all too much money to start with. That's $1,000 a day. Yeah, I should have done that.
Yeah, that's way too much for this.
Hmm.
Give a few more days and it'll be.
Yeah. So you would have made 10,000. Well, I did a bad job making my example. Right? If I'd have let you work 4 weeks, then the next day you would have made $10,485.76 on day 22. Day 23, you would have made $20,000.971.
21 days was just below what you.
It was just below 41,943. If you double it again, 83,88608. You get the idea? It was way closer than it should have been. Next time I'll know. I'm not paying you $1,000 a day. I'll pay you $100 a day. How about that?
Like in all seriousness, you need somebody to market.
No,
I'm paying $100 now to stay in my current.
I'm not paying anybody nothing. You know how much money I spent on the Field of Nightmares? Yeah. I can't even tell you how much. I wouldn't even have a good guess. Okay, so anyways, right there, I've graphed 2 to the x. Well, I've recorded myself this whole time. That's wonderful. Okay. Now next, let's also graph 4 to the x. So let's go y equals. Let's go down to y2. Y2 should be 4 to the x. If you graph it, when I graph mine, mine's in red. When I click the graph button, so you can see the shape of the graph is very similar. Right? We still have that same horizontal asymptote here, where it's going to be really small, and then it starts to grow exponentially. Right? So this would be the example where I was timesing your pay by 4 times every day, instead of doubling it every day. Right, 2 to the x is doubling. Right here, 4 to the x, that would be 4 times your pay. So on the first day, they made 4. The second day, they made 16. Third day was 64, and so on. But it's just kind of like we stretch the graph, right? If you go back to what we were doing before. So the graphs of these are very similar. You put this in your calculator. So you guys graph both of those. Does everybody feel good about it? Okay, so when I graph them, this is what it looks like. Let's do that same general form. So whenever we have a positive x, that's our exponent. You can see what the graph does there. Think about before we graph it, what do we think these are going to do? So we have 2 to the negative x and 4 to the negative x. So before you graph it, think, what's the graph going to look like? Well, basically what my exponents were when I was plugging in -2, -1. Now when I plug in -2, this is going to be 2 to the positive second, right? So does anybody have a guess what the graph's going to look like? Exponential decay. Sure, I like that explanation. It's a little fancier than what I was expecting. Right? Yes. Yes. Where it used to be growing as my x's get bigger, now it's going to be shrinking as my x's get bigger. So when I graph 2 to the negative x, right here's what that graph looks like. And then if I graph 2 to the negative x and 4 to the negative x on the same graph, again, we can see it still follows that similar pattern. Negative is being a reflection over the y-axis, right? I'm changing the signs of all my x's. That was a reflection. So when you look here, let's, again, try to anticipate what we think is going to happen. 4 raised to the x minus 2. Does anybody have a guess what they think this graph would look like? Before you graph it, think back to our transformations. What's happening? Is this happening inside or outside the function? It's inside. It's in the exponent. That's inside the function. So inside affects the x's. So that means this minus 2 is going to shift the graph right 2. Right? They do the opposite of what you think on the inside. That'd be my guess. So now let's graph it. If I graph 4 raised to the x. Oh, sorry, I messed up. 4 raised to the x minus 2. Graph it. It's like it's delayed its time that it's going to start growing exponentially, right? It shifted it right to. Right, what do we think this is going to do? This inside or outside? Outside. So it's going to affect the y's. So if I graph this, I bet it's going to go up 3. Right? Those same type transformations we've been dealing with before. If I graph that one, you can see my horizontal asymptote's in a different place now. Right? It's up higher. It's now getting closer and closer to 3 instead of the y-axis. And then here, you graph this one has 2 transformations. This is going to be a reflection, and then this is going to go down 3, right? Graph it to confirm it. 4 raised to the negative x. But it's just cool to see all those things that we've learned about with other functions. Well, they still hold true here, right? I mean, there's no exceptions to those rules. So again, I don't focus so much on the graphing of these. It's not my favorite part, right? But it's just good to see those things still come into play with our exponential functions. Will be your best friend in calculus. Okay? But we're going to have to try to explain it to you in a way that doesn't involve calculus. So let's do that. It says, for many applications, the convenient choice for a base is the irrational number e, which is 2.71828128. So again, what's irrational number? What does irrational mean?
I used to know, but I forgot.
That means it's a root of a number, or the square.
Okay, it could be the square root of an integer that's not a perfect square. How about this? What is a rational number? What word is in rational? Ratio. Ratio is fraction. A rational number can be written as a fraction of 2 whole numbers. Whole number over whole number. That is a rational number. So an irrational number cannot do that. What's the one irrational number you've worked with the most? Can't be written as a fraction. 0 can be written as a fraction.
So 0 under radical.
It's still 0.
Oh.
Well, those are imaginary. Those are not irrational. Negative under radical is imaginary numbers. What is pi? 3.14159264912. Right? It's a number that is a decimal that goes forever. It never stops, never repeats. That's an irrational number. Okay, well this is the most famous irrational number probably ever. It's definitely the most useful in geometry, right? And in trigonometry. In calculus, this is the most favorite irrational number, e, which is this number here. It's just kind of like pi. It's a number that never stops. The dot, dot, dot keeps going, but we're just rounding it. This number is called the natural base. A function f of x that is written as e, so that's that number, 2.71828128, raised to the x. This is called the natural exponential function. And its graph is shown in figure 3.9. The graph of the natural exponential function has the same basic characteristics as the graph of all of our other functions, right? We talked about 2 to the x, look very similar to 4 to the x. So it's very similar to 9 to the x, right? They're just little different numbers where they happen. So this e to the x looks just like them. Be sure you see that the natural exponential function f of x equals e to the x, e is a constant. E is just a number. E never changes. But x does change. So let's look. What makes e so cool, so unique? Okay, well, if you make that chart, if I plug in 0, e to the 0 is 1. E to the first is e. Alright, so remember how we made that chart before. -2, -1, 0, 1, and 2. E to the 0 was 1. E to the first is e. Right here, -1, this would be 1 over e. This would be 1 over e squared. This would be e squared. Okay? Now, in example 5, you'll see that for large values x, the number e can be approximated to be 1 plus 1 over x to the x. So, again, I guess they're not going to explain. I thought they were going to do the big of your calculators. Have mine and have yours. You're going to need to know where this E button is, depending on which calculator you're using. I'll show you on mine, my calculator. It's Shift, and it's the button beside the 4 that says LN, stands for natural log. Okay, we're going to look at those later this chapter. Okay, but I have E raised to the X, so I click second, natural log. You can see I have the button E comes up, and it has E raised to, it automatically has an exponent, right? So E raised to the X, so if I plug in an X value being -2, I click enter. E to the -2 is 0.13533352832. Everybody get that value? Again, that's rounded because E is an irrational number. Okay, let's see on your Casios. I know the majority of you have Casios. It's in the same position. It's Shift natural log. It's on the top right on those calculators. You see them? Your E raised to the... Okay. Is there anybody else that doesn't have a Casio? You get a Casio? You didn't have one before, did you? Okay, got you. I was coming to find where it was on the Texas Instrument. Because I don't remember. It's been a while since I've used that old Texas Instrument. Okay, so let's practice plugging in the values just to make sure we know what we're doing. Okay, if I plug in E raised to the 0.25. Get this here. So if we feel good about plugging them in, finding where E is. I need to go through all these. That's really boring to me. You could actually use would be your compound interest formula. So one of the most familiar examples of exponential growth is an investment earning continuously compounded interest. Suppose a principal P is invested at an annual interest rate R, compounded once a year. If the interest is added to the principal at the end of the year, then the new balance is P sub 1, which is the old principal plus the principal that you earned in interest, which we can find this as 1 plus R. This pattern of multiplying the previous principal by 1 plus R is repeated. That really doesn't matter to you. I don't really feel like... most banks and things that you invest in, or even if you're borrowing money, most of the times those use what we call simple interest. So that means the interest is kind of separate from the principal. So let me just make an easy example. Say that I invested $1,000 and I was getting 10% back. Okay? I just made those numbers because that's easy to deal with. Okay, so the first year I make 10% on my $1,000. So let's see, this is year, and this is amount. So at year 0, I have put in $1,000, and I expect every year for it to grow at 10%. Okay, that means the next year I would have $1,100. The next year I would make 10%, but I'm still just making 10% on the original amount that I invested. So now I've earned another $100. Year 3, I've earned another $100. Year 4 is another $100, and so on. Okay, that's at 10%. This is called simple interest. Okay, compound interest, that is where your interest makes money. So if I do the same example, but I'm doing compound interest, and again, let's just do it once a year. Then let's say at year 0, I still invest $1,000. Year 1, if I make 10%, I'm still going to have $1,100. Okay? But now year 2, I'm going to make 10% on this new amount. I'm no longer making 10% on the original amount. So 10% here would be $110, which means the next year I'm going to have $1,210. So my interest made money, where here I just kept making interest on the original, is the difference. Then the next year, 3, if I make 10%, that would be $121 that I made. So that would be 1,331. The next year, if I make 10%, that would be $133. So that's 1,436,1. So again, on a small scale, I mean, again, not a huge difference, right? But over 4 years, I've got an additional $62 because I'm making interest on my interest. So we'll look at those problems tomorrow. That's the difference between simple interest and compound interest, though. So when I look right here, these are our 2 different compound interest formulas. So depending on the problem, that lets us know which formula to use. So the top one here is anytime we're compounding anything besides continuously. So if we're compounding monthly, if we're compounding annually, if we're compounding semi-annually, semi-monthly, or whatever terminology they use, could be daily, we're going to use this formula. So A equals the amount we have in the bank or whatever, it's our amount, equals the principal. Does everybody know what a principal amount is? Yes, no, no, yes?
No.
It's the amount that you either invest up front or it's the amount that you are borrowing. So if you're borrowing money, that would be the principal amount. It's how much you borrowed. Or if you were making a down payment on a house, that would be the principal amount, the amount that you put down. Okay, that's a lump sum. And that's 1 plus R represents the rate. And the rate always has to be a decimal. So if we're going to be given a percentage most of the time. So if it's an 8% rate, then that's 0.08. Right? 7.5%, 0.075. Right? Just got to make that a decimal. N represents the number of times it's compounded in a year. So if it was annually, that means it's once a year. So my N would be 1. If it's monthly, my N would be 12. If it's daily, my N would be 365. Okay, it tells us in the problem how often it's compounded. That's the N. And then the parentheses are raised to the N, that's the same N, times T. T represents the amount of time in years that it's going to be invested, that you have to pay back the loan, whatever the question is. T is time in years. Any questions on this formula? Now the second one simplifies the formula some. This is anytime I have continuous compounding. So it'll say compounded continuously. So that means basically my N is going to infinity, right? It's almost infinite. Yeah.
What is P and R?
P is the principal amount. It's the amount that you are investing or the amount you are borrowing. R is the rate. And it's going to probably be given to you as a percentage. You'll have to make it a decimal. Okay, then this one here, like I was saying, this is continuous compounding. So what basically is happening is my n is going to infinity because it's continuously being compounded. That's the amount is equal to the principal times e raised to the rate times time. Okay, so it kind of simplifies the formula whenever you have continuous compounding. Another reason we like continuous compounding, I guess I should point out, this e is the e we looked at yesterday. That's the natural number, e. Okay, so here's my problem. I want you guys to try to identify what all of my variables are. So look up there and see if you can tell what is the... Okay, so what's the 9,000? That is the P. P is 9,000. What is 2.5?
R.
It is the R. So I would want to make that into a decimal. So 2.5% is 0.025. And what else do we see here? We have compounded annually. So that's telling me how many times it's compounded. So that means N is 1. Right? N represents how many times it's compounded in a year. In this case, that would be 1.
So what is the 5? 5 years.
And what is the 5? It's the time. It's the T. And time always has to be in years. So because this is compounded annually, which formula do I need to use? The top one or the bottom one from the last page? The top one, right? The bottom one is only for continuous compounding. So I've got A equals P times 1 plus R over N raised to the N T. And I'm going to substitute in. It tells me to find the balance. That means I'm looking for the amount. So I'm looking for A. So that's good news because A is already isolated. So it's going to be 9,000 times 1 plus R, which is 0.025, over N, which is 1, raised to the N, which is 1, times T, which is 5. And so we want to plug all that into our calculator. So I would recommend you practice doing this now because you may, not put the parenthesis where you're supposed to, or you may leave out something. Okay, I've got it plugged into this Texas Instrument. Like I said, you may want to use your calculator. But that's the value that I got. $10,182.67. And again, when we're doing these money problems, we always want to round to 2 decimal places, right? Because that's how much money we use. 2 decimal places. I got it plugged in. That's what we should have gotten. $11,520.76. Compounded more frequently. So right here, we have a total of $12,000 that's invested at an annual interest rate of 3%. Find the balance after 4 years when the interest is compounded, A, quarterly versus B, continuously. So we have two problems here. One of them is compounded quarterly, the other compounded continuously. So let's set up the variables that we know are the same every time. Since $12,000 is invested, that is my principal amount. 3% is my rate. The time is 4 years. And then here, if I'm compounding it quarterly, in that problem, my n's going to be 4. In the second problem, my n is infinite, right? Because it's continuously. So we have to use the other formula for B part. So let's set this up here with the same formula we've been using, which is A equals P times 1 plus R over N raised to the NT. So that's going to give me A equals the principal, which is 12,000, times 1 plus the rate, 0.03 over N, which is 4, raised to the N, which is 4 times T, which is 4. So I'm going to plug all that in. And like I said, I'm asking you again, please practice plugging this in. If you don't, and then you mess it up on test day, I have no sympathy for you. Okay, so when I plugged it in, this is what I got. $13,523.90. I think it's 91 cents. Yep, went around. Okay, that looks correct. Now, let's plug into the other one, which is compounded continuously. So, in that formula, I've got A equals PERT, P times E raised to the RT. So substituting in, I get A equals the principal, which is 12,000, times E raised to the R, which is 0.03, times T, which is 4. Okay. Now when I plug that in, I got $13,529.96. So it's an additional almost $6. So the more times it's compounded, the more money you will make if everything else stays the same, right? If you have the same rate, you have the same amount of time, then as the compounding increases, so will your final amount. The problem here says, let Y represent a mass in grams of radioactive, thank you, 90 SR, whose half-life is about 29 years. The quantity of strontium present after T years is given by the formula Y equals 10 times 1/2 raised to the T over 29. And then it wants to know, A, what is the initial mass? So at the very beginning, the initial mass always is when T is 0, right? Because no years have elapsed. So when I plug that in, I'm basically going to take this and I'm going to plug in 0 for t. So that's y equals 10 times 1/2 raised to the 0 divided by 29. Okay, well 0 divided by 20. So again, you can put this straight in your calculator. I don't have to though, because 0 over 29 is 0. 1/2 to the 0 power is 1. So at the very beginning, my y should be 10. Right? So you can do that from your calculator, or I didn't have to use my calculator on that one because I got an exponent of 0. Anything to the 0 power is 1. B part, how much of the initial mass is present after 80 years? So now we're looking at y equals 10 times 1/2 raised to the, now if I'm looking at 80 years, it's going to be 80 divided by 29. This one I am going to have to use my calculator on. So I'm plugging in 10 times 1/2 raised to the, and that's going to be 80 divided by 29. So when I did that, I got 1.4776. And they rounded that to be about 1.48 grams. Okay. Your answer? I hope so. Sounds like we are. What'd you guys get?
0.2183458.
What's the book had? About 0.22 grams. Okay, so we used it there for radioactive decay. We've used it for compound interest. They also use this for population growth. So the approximate number of fruit flies in an experimental population after t hours is given by the formula Q of t equals 20 times e raised to the 0.03 t as long as time is greater than or equal to 0. So you have negative time. So we want to find the initial number of fruit flies in the population. So what they're wanting to know is, how many fruit flies did we start with? Well, at the beginning, what is time? 0. Boy, we're in trouble on these problems. So the initial means at the start, where time is 0. So I'm going to use the formula. I'm going to plug in 0 for t. So that's going to give me Q of 0, which is 20 times e raised to the 0.03 times 0. So again, you can plug that straight in your calculator. I know that 0.03 times 0 is 0. I know anything to the 0 power is 1. So that means there are 20 fruit flies at the beginning, starting with 20. Questions there? B part wants to know, how large is the population after 72 hours? So they tell me here every hour represents t. T is how many hours we have been. So I'm going to look at Q of 72 this time because I'm 72 hours in. So that would be 20 times e raised to the 0.03 times 20. Okay, so that I am putting in my calculator. It is 72, obviously. Well, why? Who said 20? Genius said 20. 20 times E. Thank goodness one person's paying attention. 20 times E raised to the 0.03 times 72. When I do that, I find Q of 72 to be 173.42. So that would be 173. Right, because we're talking about number of fruit flies. Does it make sense to have 0.42 fruit flies? No. Maybe if you swatted one of them, right? But you haven't. Okay. So there are 173 fruit flies just 3 hours later. Or sorry, 3 days later. 3 days. 72 hours later, which is 3 days. Okay? And then C part tells me to graph this. So we're going to use our graphing calculator. So I'm going y equals, I guess y'all need a graphing calculator. Okay, we're just going to enter that formula in for y equals. So I've got y equals 20 times e raised to the 0.03 times t, which is 70, well, I don't know what t is going to be, right? So it's going to be times t, which is my variable. So I'm going to put that in as an x in this problem. So I've got 20 times e raised to the 0.03 times x. So just so everybody can see what I have here. That's what it looks like on my graph. Second, and then natural log, which is beside the 4. Okay, everybody get that entered into your graph? Okay, now then I click graph. Everybody can see what my graph look like here. It's wonderful.
Yeah, I got nothing.
You got something. It's just not on the graph. Huh? Yeah, it's on the graph. Because we know what should happen here. When time is 0, what is my y value? It is 20. So I've got to be up here, right? I know my graph should be happening up here. Also, it told me time had to be greater than or equal to 0. Right? It doesn't make sense to have negative time. So I'm going to go fix my range, right? The things I'm looking at on my graph. And I know that I need to start at 0. I'm going to go to the right. And I'm going to have very high numbers. Because I know that, again, t is in hours. So I'm clicking window. My x minimum, it doesn't make sense to have less than 0. So I'm putting in 0 there. My x maximum. Well, we were looking at 72 hours out, right? Which is only 3 days. So I'm just going to make my x max 100. So that puts me at 100 hours out. X scale. Let's go by tens. So every tick mark represents 10 that way. Then my y minimum. Okay. Well, I know that I'm not going to have a negative number of fruit flies. So I'm going to put my y minimum to be 0. Then y maximum. So I know it's going to start at 20. I know 72 hours later I'm at 160 whatever. So let's put our y max at 250. Right? And let's say that the y scale, let's put it by 25s. So that means every tick mark represents 25 on the graph. So then when I graph it, I'm going to have a much more meaningful graph. I can see a lot more what's going on. So again, it's growing exponentially because it's an exponential function. But I can see, I know that this represents 25. Well, I know I started at 20 fruit flies. Right, so that's right about what I'm thinking. And this is every 10 hours how it's growing. The first 10 hours, not a lot of growth. Next 10, a little bit more, but not a lot. Next 10. All right, we're starting to pick up. And then here at the end, look at the difference between every 10 hours. It's really starting to take off. It's got that exponential growth to it, like an exponential function. All right? Oh, gosh. So when I graph those, on the same graph, it kind of fits the bill of what I was saying. So I left the same window. I didn't change anything. I see that the blue one started off with 20, or this one started with 10. And so because this one started with fewer, this one's growth happens more quickly than this one does. This one's going to take a little bit of time. It's going to eventually turn into that same model if I keep zooming out, where it grows exponentially.